that okay. So now let's see. The idea of parameterization, I will repeat, is basically the process whereby you solve an equation. That's not a very good description. So I will repeat myself again. When you are asked to solve a system of equations, which can consist of a single equation, you are trying to find a parameterization of the solution set. Parameterization of the set defined by the system of equations. That's what you are doing. So now in linear algebra, we solved systems of linear equations. So let's take in 3 dimensions. So suppose I give you this: solve x plus y minus z is equal to 1. Solve the system. And x minus y plus z is equal to 1. So these are clearly independent equations. I'm not going to bother talking about that anymore. So number of equations is equal to 2 in R3. We are solving this in R3. So dimension of R3 is equal to 3. So number of parameters is equal to dimension of R3 minus the number of independent equations is equal to 3 minus 2 is equal to 1. So these are 2 planes, each is a plane, and they intersect and define a line. So the set that we are talking about is S, which is defined to be the set of x, y, z in R3 such that x plus y minus z is equal to 1 and x minus y plus z is equal to 1. Oh, this became a bit messy. Okay, S is equal to x, y, z in R3 such that x plus y minus z is equal to 1 and x minus y plus z is equal to 1. This is the set. And if I were to solve it, what would happen? Solving such an equation is extremely easy. So the augmented matrix of the system is equal to 1, 1, minus 1, 1, minus 1, 1, 1, 1. So we row reduce row 2 replaced with row 2 minus row 1. So that gives me 1 minus 1 is minus 2. 1 minus minus 1 is 2. 1 minus 1 is 0. So that means now I can replace row 2 with half row 2. So that means we have 1, 1 minus 1, 1, 0 minus 1, 1, 0. So now I have to kill this one. So row 1 replaced with row 1 plus row 2. And row 2 replaced with minus 1 times row 2. So this gives me 1, 0, 0, 1, and 0, 0, 1, minus 1, 0. So this is very simple. It means that x is equal to, from this I conclude that x is equal to 1 and y is equal to minus z, right? So which means x is equal to 1, y is equal to minus t, z is equal to t. So that means, and t is a real number. So that means x, y, z is equal to 1, 0, 0 plus t times 0 minus 1, 1. Okay, all this you know very well. So what does this mean? So this is where the idea of the math. So we have found a solution which is expressed with a single parameter, right? The single parameter is t. Okay, so now comes the remarks from which you should understand what is going on. So you have two planes. Can you see me? So there are two planes which are intersecting in a point. No, I am not doing it properly. Yes. You see, my two hands are two planes and they are intersecting where the hands meet. So these two planes intersect in a line, not a point. So there are two planes that intersect in a line. But what is the primordial idea of a line? The primordial idea of a line is the one-dimensional real number, system of real numbers. That's the primordial idea of a line. So this is three-dimensional space. So which I will draw x-axis, y-axis, z-axis, and there's a line sitting in it somewhere. Okay, that line we want to imagine as a map of the primordial idea of a line, which is the real number. So the primordial line idea of a one-dimensional flat space is the real number. The primordial idea of a two-dimensional flat space is R2, which is the plane. The primordial idea of an n-dimensional flat space is Rn. So if the solution is a one-dimensional flat space, we want to see how it sits inside R3. So what we are going to do, and this is the idea of the mapping. So we want to think of this line as the following, that I have a line over here and I have a three-dimensional screen over here. I want to know that the line that I have over there, how it is mapped from here. So the point, this is the point 0, that must go to some point in the line. Okay, so what does 0 go to? That's very simple. How do you find where? So this is the point 0, right? So 0 means t is equal to 0. So this is the point t is equal to 0. Now, x, y, z, x, y, z is equal to, with t replaced with 0. Sorry, this is the wrong kind of bracket. Oh, this is the eraser. I have to have pointy bracket. Oh, just a moment. Yeah, is equal to, what was it? 100, 100, 100 plus 0 times 0 minus 1, 1. So which is of course equal to 100. Okay, so 100, so this picture is not very good. I mean, I have to make a more realistic picture. Incidentally, one can write a program that would do this. In real time. Maybe Arash can be recruited to do that. 100 is this point, right? So this point is mapped onto this point. What about t is equal to 1? Where does it go? So x, y, z, t replaced with 1 is equal to 100 plus 1 times 0 minus 1, 1 is equal to 1 minus 1, 1. Okay, 1 minus 1, 1. Which point will that be? So 1 minus 1 is this way, 1. So that's this point. So my picture, so this is the point 100. And this is the point, what was the point? 1 minus 1, 1. 1 minus 1, 1. So this is the image of this point, 1. T is equal to 1. So this point goes there. So in order to draw a line, you just need 2 points, right? And then you connect them. So the line that I had drawn actually looks like this. It is this line. So the mapping tells us exactly how it sits in free space. Okay, so the whole idea of parameterization is that you can locate every point on the line with respect to the primordial idea of a line. Is this clear? This idea? So you have to imagine this geometry in your heads. So you can think of this as a screen, a three-dimensional screen, and you are shining a flashlight. So the point 0 goes to the point 100, and you're moving the flashlight along the line, and that traces out the line. Is this completely clear? Okay, let's do another example so that you understand. You see, this is the part that you are supposed to do on your own when you read the notes. Because even now, I have a certain image in my mind, right? I can't transmit that image to you. I can use words to form a crude approximation of what is going on in my head. And somehow you have to exercise your imagination in order to understand what that image is like, and something happens in your brain that allows you to construct something similar. These are all sort of crude hints as to what the thing is. So the functional form, which I write as follows, that lambda sends t to what should it be? 1 plus, just a minute, go back. Yeah. Is equal to how much? What is it? This is 1 minus t, right? So the functional form is t going to 1 minus t from R to R3. This is the functional form. And S is equal to the image of lambda. Right? That is what you know from MATH270. So this just simply means that I am telling you where a particular point on the line, T, goes in the screen, which is R3. This is the picture that you have to keep in mind. So there are 5 or 6 different ways of describing flats. And this is one of them. This is the parameterization. This makes the parameterization come to life. So unless you have a geometric understanding of what it is, you really can't, you navigate in the dark. Is this clear? Let's do another example of a similar sort, just so that the idea is there. So solve x plus y plus z is equal to 1. Actually, let me write this. Yes, w plus x plus y is equal to 1 and x plus y plus z is equal to 1 in R4, sorry. Okay. Again, as before, the number of independent equations is equal to 2. Dimension of R4 is equal to 4. Therefore, number of parameters is equal to, oh, sorry. Is equal to 4 minus 2, which is equal to 2. So the solution set is a 2-flat. Okay, what is the primordial idea of a 2-flat? It's R2, right? So we have to somehow understand the solution as R2 sitting inside R4, which is a flat. Okay, so R2 sitting inside R4. How do we get that? Well, we do the same thing as before. The augmented matrix of the system is equal to 1, 1, 0, 0, 1, 1, 1, 0, and 0, 1, 1, 1, 1, 1, right? Row 1 replaced with row 1 minus row 2. So that gives me 1, 0, 0, 0, 1, and 0, 1, 1, 1, oh, 0. Is this 0? Yeah. What happened? Zero, 1. Did I make a mistake or is this okay?
Shouldn't the last one be -1?
-1, yes. There's nothing called -1. -1. 1 is the name of exactly one number. Okay, so that solves the thing. So that means W is equal to WXYZ. So W is equal to Z. And this one is Y, right? No, X is equal to 1 minus Y minus Z, which means W is equal to T. W is equal to T. X is equal to 1 minus S minus T. Y is equal to S. Z is equal to T. S and T are in R2. Right? This is obvious from our understanding of linear algebra. So that means WXYZ is equal to 0, 1, 0, 0 plus S times 0 minus 1, 1, 0 plus T times 1 minus 1, 0, 1. Okay? Clear? So that means what? That means this is equal to, let me write this down, T 1 minus S minus T, 1 minus S minus T. T. Oh, S, yeah. And the last one, just T. Last one is T, right? So that means lambda is equal to ST going to T 1 minus S minus T ST from R2 to R4. So now note that an image of lambda is equal to S. The solution set, which I didn't write down in this case, but doesn't matter. I mean, I can write it down. S is defined to be equal to WXYZ in R4, such that W plus X plus Y is equal to 1 and X plus Y plus Z is equal to 1. So let's see what lambda does to. So lambda of ST is equal to T. T 1 minus S minus T ST. So for instance, lambda of 0, 0 is equal to 0, 1, 0, 0. Lambda of 1, 0 is equal to 1, 0. Oh, just a moment, I made a mistake. T is 0, so this is 0. 0, 0, 0, 0, S is 1, 0. And lambda of 0, 1 is equal to 0, 0, 0, 1. We have, oh, it's set like this. There's a timer over there. It just went dark. So, okay, so now we are in a position to understand what is going on. So note that in this case, my primordial setup is R2. So this is R2, right? So this is what I'm going to map into a 4-dimensional space, which I, of course, can't really draw. So that's why I'm going to pretend that I can draw. So this is W, X, Y, Z. Of course, we can't fit 3 perpendicular things onto a plane, but we shall pretend that the angles are 90 degrees. So what is this saying? This is saying that 0, 0 goes to the point 0, 1, 0, 0. 0, 1, 0, 0. So that this is the point 0, 1, 0, 0, right? So this is 0, 1, 0, 0. Now 0, 0, 1, 0. 0, 0, 1, 0. So that's here, right? 0, 1, 0, 0. And 0, 0, 1. Oh, 0, 0, 1, 0. 0, 0, 1, 0. And then what's the other one? 0, 0, 0, 1. 0, 0, 0, 1 is here. 0, 0, 0, 1. So now, this point, the origin, which is 0, 0, so this is 1, 0, this is 0, 1, this is 0, 0, right? So 0, 0 goes to which point? 0, 0 has moved to 0, 1, 0, 0, right? This has been mapped to this point. 1, 0 has been mapped to which point? 0, 0, 1, 0. So 1, 0 has been mapped to this point. And 0, 1 has been mapped to this point. So which means that these two span the flat. So effectively, the two flat looks like this. It's the span of these two vectors. So it's a picture of R2 in R4. So if I move around here and somehow there's a flashlight that gives the corresponding point, I will move around over here. So the solution says, go to this point, and from that point, take S steps along one of these and T steps along another of them, and that way you can go everywhere. Is this idea clear? Okay. You will have to contemplate this situation to get the picture clear in your head. It's an infinite, unbounded plane which sits in a particular way. And this mapping tells you how it sits over there. Okay. So it is presented as an intersection of 2 3-flats in R4. And the improvement is that now I know exactly what the coordinates of any point on the plane will have to be in terms of the parameters S and T. So the equational description makes it easy to know where exactly if one point is not in the set or not. The parametric description makes it easy to know exactly what a point is in the set looks like. It produces a coordinate system, but this is global. Everywhere this is the case. This will no longer be the case if the equations are no longer linear. Okay, so this is the most important point to understand. Let me pause for a moment. Does anyone have any questions? Yeah.
This is an intersection of 2 or 3.
No, the set S, which I started with, defined by the two equations, is presented as an intersection of 2 3-flats. Why are they 3 flats? One of them, so let me write that down. S is equal to WXYZ in R4 such that W plus X plus Y is equal to 1 and X plus Y plus Z is equal to 1, which is equal to, this is an intersection of 2 1-flats, 2 3-flats, sorry, WXYZ in R4 such that W plus X plus Y is equal to 1, intersect WXYZ in R4 such that X plus Y plus Z is equal to 1. Right? This is and, so that becomes an intersection. Okay. This set is defined by one equation. Therefore, the number of parameters needed for this one will be 4 minus 1, which is equal to 3. So this is a 3-flat. This also is defined by one equation, so that is also a 3-flat. These 2 3-flats intersect in a 2-flat. And that 2-flat is precisely what we found. Is this idea clear? Okay?
Yes.
Okay. So this is the picture that you should keep in mind. Now, this gives you a global parameterization, which means that anywhere on this flat, this 2-flat, you want to go to will be characterized by a certain pair of numbers, S and T. So I will repeat what it is saying in ordinary words. So the first way the solution, okay, the first description of the solution says that from the origin, go to the tip of the point 0, 1, 0, 0. And from that, take S steps along the vector 0, minus 1, 1, 0, and T steps along the vector 1, minus 1, 0, 1. That brings you the point to the point ST. So depending on the number of steps you take, you can go to any point in that flat. Clear? So it's presented as an intersection of 2 3-flats, but it is actually a 2-flat, And you can go anywhere over there using this. If I ask you if is the point 1, 1, 1, 1 in that flat, the answer is no, because 1 plus 1 plus 1 is equal to 3, which is not equal to 1. So it doesn't satisfy one of the equations, therefore it is not in there. Okay?
Is it like possible to like visually conceptualize it, or no, because it's in 4 dimensions?
I mean, I don't know what to say to that because I can imagine it. So, except that, I mean, it sits somewhere, but I can't really imagine 4 axes perpendicular to each other, but I am sufficiently used to thinking in this manner so that it provides me with a picture of some sort. How exactly it is coded in my brain, I do not know. Okay, but I mean, visualize probably is not the best word to use. One should use the word imagine. Okay. No, but it takes time. It really takes time. But this sort of thing is, you know what happened? I went, it's because Max asked that is this a question of just looking up on the internet? So I went and looked up on the internet about this intersection of 3 cylinders. And what I found was that a lot of things are available, including a picture. But I would like you to make a papier-mâché model of it. So which should not be very difficult. So I will come to that in a moment. But I also found some astonishing things, which means that absolute trivialities are being published in journals. So intersection of what did we do in class? Intersection of 2 ellipses, right? Someone has written a paper about it and got it published. That took how long? Maybe half an hour at the most. I mean, the standards in the United States have come to somewhere near minus infinity. Though that I could have done when I was 14 years old, it could be given as a problem. How can someone publish this? I mean, I was really astonished. Anyway, the point that I want to make is that you can look things up on the internet, but you will have to cast it into a form that fits the setup that I'm describing to you. Otherwise, you will not get any points. I mean, I saw people have, there was an awful video of someone calculating the volume of the intersection of 3 cylinders. So from that, of course, you will get the answer, but it is really off. So when you look at the internet and get stuff from there, be very, very careful, because there's an enormous amount of trash. I will send you the papers. I mean, I didn't save them, but I will send you the papers so that you see. We solved 2 problems last time. These were of, so the number of parameters 0, right? Because they were just a bunch of discrete points. And I solved a problem with 1 parameter now, another problem with 2 parameters, right? Today, so far. But these were all linear. What we did last time were actually not linear, right? Because it was 2 ellipses and then 2 parabolas intersecting. Okay, so now let's complicate our lives a little bit. Let's talk about the circle. So, yes, well, I don't really know what is in the notes anymore because I wrote them long ago while I was in quarantine, and I never go and read them unless someone tells me that there's some glitch somewhere. But this should be in the notes, but I'm not going to describe what is in the notes because the notes give you parameterization, but now I want to describe to you the thinking process that leads to parameterizations. So this is the circle. Oh, one other thing. I was alarmed by your lack of familiarity with the the shapes of objects defined by the equations. I told you that there are 3 or 4 pages in the book, Mathematical Handbook, which all of you should get. Okay. And the Mathematical Handbook has pictures and the equations, and you must familiarize yourself with all of them.
Is it in the bookstore or online?
You should buy it online. I don't know. I mean, I don't really know where the bookstore has got it. In general, always compare the prices before you buy something.
Yeah.
Okay. And Sean's outlines are very old. So if you buy an old edition, you can get it for 25 cents. I doubt if the bookstore will sell something for 25 cents. Okay. Oh, there's one. I just saw that the Barnes & Noble on Walnut is moving and everything is 30 to 50% off. So you could go there and see. They used to have some Sean's outlines, but they certainly should have the manga guide to linear algebra. That's the cartoon guide. The Japanese cartoon, very good quality. I didn't read it, so they tend to be a little on the violent side, but I don't think one can be too violent with linear algebra. But anyway, so now remember again, what did I say? What is our idea of a one-dimensional object? What is the primordial idea of a one-dimensional object?
That's a line.
Line. Yeah, that means the real number line, the real line. Okay, this is a one-dimensional object, right? The circle, I don't mean the disk, not the inside, just the circle. So the parametric solution would be a way of mapping not the whole line, which is unbounded. This is a bounded object. So the parametrization would be the map which tells me how to bend it into the form of a circle. But if you have, so we shouldn't think of the whole line, but an interval. Right? So interval, we will always choose the interval to go from 0 to 1. Okay? And somehow we have to bend the interval in the form of a circle. So now I'm going to do it geometrically. So let's say okay. Obviously, an interval has 2 ends, right? If an interval has 2 ends, I can't bend it in such a way that the mapping, the parametrization mapping is injective and the 2 ends remain separate and the image is a circle. It can't happen. No. So, I mean, if I want to put the 2 ends together, that means that the map is not injective, right? Because the 2 ends are 2 different points, they come to the same point. So, but the parametrization has to be injected. In fact, it must be a bijection onto a patch. Otherwise, we'll not be able to do any calculations with it at all. So what would one do? So one would take, can everyone see me? Yeah. Suppose I have a piece of string. Does anyone have a piece of string? Actually, you have a what? Charger, yes. That will do. Okay. This is my primordial idea of an interval. So what would I do? I would just do this, right? That will give me a circle. So I take this and just bend it this way. But this has to be written as a map. Okay, so don't use the charger, take the charger. So what I'm going to do is this. This is the circle. And let's just a minute. Why is it not erasing? Okay. This is the circle. Let's say this is the interval. Okay, so now I want to, this point remains this point remains this point goes here, this point goes here, this point goes here, etc. This is going to be my mapping. Do you understand? Every point is going to exactly one point. So I'm getting the top half of the circle from this mapping. Later on, I'm just describing in a completely informal manner what I'm trying to do. Okay. So I will somehow have to calculate on the basis of this picture what a point T is going to. So let's try the following. This is what someone who is trying to make a circle out of a wire would actually do. So the interval in this case, let's say, is from the point 1 to the point -1. So this is the origin. So this is the x-axis. This is the y-axis. Okay. So if this point is T, and if I erect a perpendicular over here, it meets this point at what? What are the coordinates of this point? So this is not terribly difficult to calculate. This is 1. This I should have turned off, but we'll ignore it. Is very long. So please excuse me. Who knows that I'm teaching? It should hang up after the 4. Yes. Okay. Okay, so this is 1 because it's a circle of radius 1. So this is 1 minus square root of 1 minus t squared, right? If this point is t, actually this is 1, 0. This is t 0 and minus 1, 0 if we are in the plane. But since it's the interval, we will just take it to be that way. So this is, so what does this mean? The coordinates of this point are t square root of 1 minus t squared. So if I take lambda to be the parameterization, t goes to t comma square root of 1 minus t squared from the interval -1, 1 to R2. Then I get the top half of the circle. The image of lambda looks like this, is equal to the set of all x, y in R2 such that x, the value of x is always, the value of y is always positive, and x lies between 1 and -1. So x, such that x lies between -1 and 1, and y is bigger than 0. Y cannot be equal to 0. That's the image of lambda, which, if I draw a picture, is this circle. Is the top half without the, yeah. So you can also do this. If you just change the square root of 1 minus t squared to -1 square root of 1 minus t squared, and you can also find out maps for this half and this half. Okay. And if you take the union of all 4, the images will cover the whole thing. Is this idea clear? Yeah. Yeah. Y will have to be less than, strictly less than 0 in the other case. So, but this is, if I were working in in the studio of an artist making jewelry, this is the kind of thing that I would do. And then one would find it through someone's eyebrow or nose or something. Okay, but the point is that now, if you write this, if you program this, and if you have the Byron said that he had a 3D printer. You have a 3D printer, right?
Yes, yes.
Yeah. Can you print this? What would you print it? I mean, what is the medium? Do you use styrofoam or what?
It's a resin. Well, I have a filament printer, which I haven't really ever gotten to work, but I got a resin printer as well. This is the entire process, but I would have to make a 3D model of it and then put it into a certain form, then put it into a program. The program then lets the printer print it. So a slicer.
I would like to see what it, I mean, if it does not cost too much money, the question is, what would it do with the intersection of the 3 cylinders? Can it be printed?
Let me see.
Well, not right now. That's going to be a term-long project for all of you to do.
Yeah, I need to pick up some more resin, but that, as long as someone else has designed it, because I don't have the full understanding of how to program it into the, into use it.
That will come gradually. That will come gradually. Okay. Yeah. So now we will do something else with the circle. Excuse me. You see, the idea was to use a finite interval with open ends. So suppose I don't take a finite interval, I take the infinite real line. So it's going in both directions. Can I somehow manage to parameterize the circle using this whole line? So somehow I have to make up a way of bending the infinite line into a bounded circle, maybe without a few points. So let's go to the North Pole and note the following. If I draw a line like this, or a line like this, there's exactly one point where it intersects this line, and there's exactly one point where it intersects this line. So if I think as t moving along the horizontal line, then I can send, oh, just a moment. I didn't mean this point, sorry. I meant this point. Note that every point of the line corresponds to exactly one point on the circle. You see? And the further, the more, as this line approaches a line that is parallel to this line, the point moves further and further away. Right? So this is basically what one could do to bend an infinite real line into a circle. Is this idea clear? But what is the map? In other words, how would you, if I tell you that this is t, how would you find the coordinates over here? So we have to draw axes. So this is x-axis. This is the point 0, 0. This is the point 0, 2, right? Because the circle is of radius 1. So if I tell you t, how would you find this point? This is a very simple exercise in algebra. You have to find the equation of this line and see where it intersects the circle. And you can also use geometry.
It's not that you,
Hmm?
I don't think it's.
Let's see. Shall we do it analytically or shall we do it geometrically? Suppose we try to do it geometrically. So I draw this. Then this angle is 90 degrees. That's a simple theorem from elementary geometry. but T is this distance. T is this distance. So I know this side. What else do I need to know? I know that this side is 2. This side is 2. If I knew this angle, then this point will have the coordinates cosine of that angle and sine of this angle, right? Okay, this one you try to figure out by yourself. So if this point has coordinates, some function of t, so we call it c of t, eta of t, then lambda should be equal to t going to c of t, eta of t, from R to R2. Okay. So you will have to find C of t and eta of t. That's a very simple geometric problem. Very, very simple geometric problem. It can be done by high school students who have had basic geometry. You can also use analytic geometry. In analytic geometry, you would find the line through the points T0 and 0,2 and see where it intersects the circle. But that's too much work. Okay. So this is another way of parameterizing the circle. Okay, but what is the simplest way? The simplest way is the following. This is the circle, x-axis, y-axis. You call T this angle, in which case this point has coordinates cosine of t, sine of t. And t, you go from 0 all the way to 2 pi. So in this case, lambda is equal to t going to cosine t, sine of t from 0 to 2 pi to R2. I forgot to put parentheses around the t throughout this lecture, and people are half asleep because they didn't tell me. Here I used parentheses, but there was another one in which I didn't use. Yes, here. Okay. Okay, so let me pause for a second and ask you if you understand the idea of parametrization. Okay, so similarly, if you want to parameterize a sphere, then this is the z-axis, x-axis, y-axis. You would try the same idea by blowing up the equatorial disk. You would push it up by various amounts, and using a procedure similar to what I did, you would get a mapping. So everywhere on the disk, the points have 2 coordinates, st, and then from st you erect a perpendicular, so that touches the ceiling, right? And the second idea will also work. If you have a sphere and you have a plane tangent to this point, if you take the North Pole and if you draw a line, you see any point from the North Pole joining any point on the plane will intersect the sphere in exactly 1 point, as with the circle. So that is another method. Okay, so all these geometric ideas you somehow need to grasp. And one of the things that you need to do when you read the notes is to, I said, draw as many pictures as possible. So in order to gain this understanding. I will pause for a moment to ask you if you have any questions. You see, so this is slightly better than writing up the notes, where it is entirely your responsibility to develop the imagination that allows you to see what is happening. Here, I am acting as an intermediary to give you some sort of a description to facilitate the formation of the right circuitry in your brain. I don't know to what extent this is successful. I mean, it is better than nothing. So I will put any questions from the people who are on Zoom, or rather who are not in the class. Everyone is on Zoom. Any questions from? No? What happened to Caesar today? He didn't show up. Jesus Flores has also disappeared. The rest of them are not to be found. Okay. So this is the basic idea. So your task is to understand how to parameterize all the objects, all the quadrics in free space, and all the equations defined by quadratic equations, all the sets defined by quadratic equations in two space. So all the conic sections and all the quadrics. For each of these, there's a picture in Mathematical Handbook. So you must familiarize yourself with the picture. And in the notes, I have described in great detail the kinds of things that would work. And some combination of the sines, cosines, and the hyperbolic sine and hyperbolic cosine essentially exhaust all of them. But for the circle, you also have a rational parameterization. And I would like you to find a geometric understanding of what the rational parameterization is. Okay, what time is it now? It's exactly 1 hour. Okay, so on the exam, you have one-dimensional objects, you have two-dimensional objects, and you also have three-dimensional objects. Okay, so now we come to the three cylinders thingy. Okay, so I will write up the question, of course, but I want to point out there are three cylinders. The vertices are the points at which the three cylinders intersect. The edges are the lines along which two cylinders intersect. Okay, and the faces are going to be bounded by the edges, and the edges are bounded by the vertices. It's not the case that any two vertices are joined by an edge. Some vertices are joined by edges, other vertices are not. So to count the number of vertices and to count the number of edges requires some effort. Okay, the proposal was that there are 8 vertices, but I didn't say whether this was true or false. And the proposal was that there are 12 faces. I again didn't say whether this was true or false. If you find an actual model, yeah, but that doesn't, no, that does not help your brain develop. And that's why it is also useful to do this. This is an intersection of 3 cylinders in 3 dimensions, right? I could ask you to find the intersection of 4 cylinders in 4 dimensions. What is the most general form of the problem? Rather than 3 or 4, you would have? No, 2. In that case, the cylinder becomes a circle. So okay. In 2 dimensions, you do not really have cylinders anymore, right? I mean, you would have pairs of lines, basically. Yeah. In 3 dimensions, you do have cylinders. I asked you to find the number of vertices, number of faces, number of edges for the set defined by the intersection of 3 cylinders in 3 dimensions. And people promptly went and looked at the internet and found the picture. And yesterday I tried to find myself as to what was available, and I found some good pictures and some calculations and one video which was absolutely off. So as far as I can, yes, someone has even calculated the area of a face. So the length of an edge, I did not see anyone having calculated that. But the question is how many edges there are first of all, and then to compute the length. Okay, so now, the internet has information about 3 dimensions. So if I change the problem to find the set, find all these properties of a set defined by the intersection of 4 cylinders in 4 space, then the internet, there are some discussions of this, but I didn't see, they will not be able to draw a picture. And they may draw a picture, but that wouldn't be particularly informative. Okay, but what is the most general for problems? 3 cylinders, 3 dimensions, 4 cylinders, 4 dimensions, then what's the most general? That's not the most general. So you see, what did I say? What was the disease from which all of you suffer? You haven't been weaned from numbers yet. So each time you have a number, you have to replace it with an unknown. So the most general problem would be find the number of vertices, number of edges, number of 2 cells, 3 cells, etc. for the intersection of n cylinders in n dimensions. When you can do that, then you can say that, yes, I understand this. Clear? And then these were called Steinmetz solids or something like this, named after a person who had studied them from Germany. And I will give you links to the papers also to show how trivial they are. I cannot believe that one can publish the solution of 2 simultaneous quadratic equations. But this comes up in signal processing, actually. This comes up in signal processing because the images have to be, how should I put it? The information that you get from scattering some sort of beam, which is probing the object that you wish to investigate, and that gives rise to a certain kind of information from which you have to deduce the shape of the object from which it was scattered. Okay, and so I gave you the example of the prostate gland, right? A prostate gland, everyone knows what the prostate gland is. All of you have one, so you should know. The prostate gland increases in size as one grows older. So the model is the urethra, and the prostate gland goes around it, is in the form roughly of a spheroid. A spheroid is an ellipsoid, one of whose cross sections is a circle. So you have a spheroid with a cylindrical hole in the middle. So as we grow older, it increases in size, which means its inner radius increases and its outer radius also increases, because it increases by growing cells on those surfaces, which means it is going to constrict the urethra, which would reduce the flow of urine. So now how do you measure this? What one does is to is to scatter ultrasound off that whole place. So they put the probe on your abdomen and they use ultrasound. And then they get the ultrasound is scattered off the object and produces a two-dimensional image. So they take many cross sections. The ultrasound is made to be incident at different angles along different planes, and one has to use some sort of a formula to put all this information together to reconstruct the volume. Okay, so this is a direct application of calculus 3. But the same kind of thing would happen if someone has a brain tumor, right? If it is here, you don't want to make an incision over there. So you again take images, in that case, X-ray images and so on, or you can also do MRI, magnetic resonance images. But the idea is the same kind of thing. You're scattering some sort of a beam of the object at different planes, and you get these scattering diagrams, and you have to, so these are cross sections. So the beam is impeded by different amounts depending on the material through which it passes. And these differences can be collected and put together. So eventually you have to get a picture. So someone has to write these programs, right? And that's not easy, not an easy task. It's a very peculiar setup in which the person who makes the incision and removes the thing on the basis of the very hard work done by the programmers and the mathematicians who write up, who develop the scattering models, is paid much more than. So this comes from a lack of appreciation of the nature of mathematics and the deductive sciences. So similarly, one of the applications of the intersection of ellipsoids that I saw yesterday was in the design of the lens, in correcting myopia and so on. So if you learn this well, there's a lot that you can do. Okay. Okay. I will send you the papers, not today. I will send them tomorrow. Oh, incidentally, I also want to remind everyone that the deadline is 23:59 hours on Monday. And since I could not devise any method whereby I could prevent people from spilling over into the grace period, I have made the rule that if you do not submit by the deadline, and if you submit later, then 10 points will be deducted from whatever you submitted. So it is, I'm trying to provide a strong disincentive. Is this clear to everyone? Okay. In order to use the grace period, there has to be some form of emergency that occurs before the deadline, of which I should be informed. Okay, note that it doesn't make any difference to the time, because if you start your exam on Tuesday and it goes on to the next Monday, is the same thing as starting the exam on Wednesday and going up to Tuesday. Is this clear? Okay. So, and you must start uploading 1 hour prior to the deadline. My computer broke down or my internet disappeared are not emergencies. So you must do this in such a way that you have a backup and you don't start 2 minutes before it is due and hope that everything will work. Clear to everyone? Okay, please put this on Discord. and say that I look like a monster when I said this, so that I meant every word. Okay? Okay. Now, let's see. So, when you finally do this problem, you would have to parameterize the faces probably from a square. So the square will have to be bent into the shape of the face in the intersection of the three cylinders. Okay? And then that would tell you how to integrate it. But I found that the people who had found this, the area of the face did not use parameterization. And then there was a lot of hand waving. So the questions to consider are the following. Are all the edges of the same length? Are all the faces of the same length? Okay, so these are the questions that you need to consider. Okay, what happens if you intersect an ellipsoid with a plane? What kind of a curve would you get? No, you can't get a parabola. Parabola is an unbounded curve. What happens if you intersect a sphere with a plane? Okay, can you prove it? You just know this from experience. Yeah, I'm asking you if you have an ellipsoid and intersect it with a plane, what would the intersection look like? Ellipsoid is like a football, an American football, sort of roughly like. The cross sections are ellipses. No, no. If you take something like the I don't have an ellipsoid here, but can you look, search for an ellipsoid on the internet? Yeah, on your phone you can.
The first line is an ellipse.
But why? But if you say that it is an ellipse, you have to prove. An ellipse is a very specific curve. Something that is oval is not necessarily an ellipse.
Yes.
An ellipsoid is roughly like an egg. An egg is more a spheroid, and it is not completely symmetric. One side is a little less curved, and one side is a bit pointy. Did you see the picture? There must be pictures of ellipsoids. An ellipsoid has, yes, yeah. So the ellipsoid, the ellipsoid has an equation x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. And if you take an arbitrary plane in 3 dimensions, it's going to have an equation of the form px plus qy plus rz is equal to s. So you have to be able to solve these two equations. And 2 equations in free space, 3 minus 2 gives you 1. So the intersection is in one-dimensional closed curve. Right? What astonished me is that people are publishing papers on this. This could be set as an exam problem. But you have to, if you claim that it's an ellipse, you will have to prove that it's an ellipse. So what about the intersection of a cylinder and a circle? Let's take the cylinder X, Y, Z, this cylinder. It's a bit, it slips a little bit, so I can't really draw very well. So you see the cylinders with the z-axis and the axis. This cylinder has the equation x squared plus y squared is equal to 1. If you intersect that with a plane in general has the equation px plus qy plus rz is equal to s. If you slice a cylinder at a slant, what would you get? Notice that if the plane is parallel to the axis of the cylinder, you get two lines as the intersection. Right? Does one see? If this is the cylinder, I'm intersecting it with a plane, I will have one line here, one line here. Right? The plane could be tangential to the cylinder, in which case you will just get one line. If you slice it perpendicular to the axis, you will get a circle. What happens if you cut it at a slant? Have you all had sausages? But an ellipse is a very specific curve. All that you can see is maybe something is like this, but that doesn't mean that it's an ellipse. What is an ellipse? Yes, that's the standard equation for an ellipse. An ellipse is, all these should be defined as loci. So an ellipse is the locus of the set of points that moves in such a way that it's the sum of its distances from 2 points is constant. So the way in which you draw an ellipse is by putting two pins and then tying a thread and then put a pencil so that the thread is taut. It's not lax. And then you move it in such a way that it remains taut. The curve that you get is an ellipse. So to prove that it is an ellipse, you may have to rotate the axis and get a point at the center of the intersection and see if the equation with respect to that point and with the axis in the plane is the standard. So this is not entirely trivial. But it can be done with the knowledge that you have. And it certainly is extraordinary that people can publish papers on this sort of elementary stuff, which has been known for hundreds of years. Yes, but people have done this before. But all of you can, I mean, when you go home, if you have a sausage or a hot dog, cut it with a knife and look at the cross section. And then the question is, it's some sort of an oval. That much we know. But is that an ellipse? There's a big difference between guessing that it is probably an ellipse and to proving that it is actually an ellipse. That it is not a circle can be proved quite easily, even experimentally. You can take the center and measure the two distances to the edges, and you will find that they are not equal. It's certainly not a circle. Okay, let me pause again and ask you if you have any questions. Are you getting the general drift of the stuff?
General, yes.
But then it has to be it has to be applied in the specific case of the problems that I've set. Okay. And now that you have three more days in which to work everything out.
You're talking about the exam?
Yes. Some of the problems are very easy. The A's are very easy.
One thing is very long.
1B, I have forgotten what 1B is. Can you tell me what it is?
Have to solve. I think it was. We had a look at it. We had to do, I think it was. A1 plus A2, that's the third. Well, it was 4 equations
Okay.
and if.
Oh, the parameterizations were given. And you had to find the equational form. 4 equations with how many parameters? 2 or 1?
I don't remember.
You don't remember, okay.
I took a slight look and I started reading the notes again.
Okay. Yeah, I mean, I don't remember what the problems are. So the very last problem, I think 3C, is a 3-dimensional object you have to parameterize. A bounded 3-dimensional object. And the intersection of the 3 cylinders is going to be the general motivating problem for the entire term. It has many uses, in many practical uses I found. Okay. So, any other questions? No? The people who are not in the classroom, do you have questions? Why is everyone silent?
I do not have any questions.
You do not have any questions. And you don't have any questions either, usual? No? All of you understand everything and will get 51 on the exam, right? Okay. Yeah, we will stop there. Okay, good. So what do? I have to go to record on this computer, record the meeting to the computer, continue. But how do I stop? Pause, stop recording.